Somewhere above the clouds of a planet you have never seen, there is a river of energy so violent it can fry electronics in seconds. It is not fire. It is not lightning. It is a belt of charged particles, moving at nearly the speed of light, trapped by a magnetic field so powerful it could strip the shielding off a spacecraft before the crew even noticed. But what is even crazier is that this is one of the smallest, weakest radiation belts in the known universe. Some belts out there could sterilize an entire moon in seconds. And by the end of this list, you will understand just how many invisible death zones are scattered across the cosmos, waiting. Earth's Van Allen belts are the ones most people have heard of. They are two donut-shaped regions of charged particles trapped by our planet's magnetic field, starting a few hundred kilometers above the surface and stretching out past 60,000 kilometers. Inside them, protons and electrons are accelerated to nearly light speed, whipping around the planet in a matter of minutes. If you were floating unprotected inside the inner belt, radiation exposure would become dangerous within hours. Discovered in 1958 during the earliest satellite missions, the belts remain the reason spacecraft must be shielded and their orbits carefully planned. But here is the unsettling part. Earth's belts are considered mild by cosmic standards. The next world on this list turns that mild danger into something almost unrecognizable. Jupiter's radiation belts are where the scale problem truly begins. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's, and it captures particles from the solar wind and from volcanic material ejected by its moon, Io, spinning them into belts far larger and far more lethal than anything Earth produces. A human standing near Jupiter's inner belt without shielding would receive a fatal radiation dose in minutes, not hours. Spacecraft engineers have had to design entire missions around avoiding the worst of it, threading narrow orbital paths just to survive long enough to gather data. Take a magnetic field, multiply it by thousands, and you get a radiation environment that treats metal like tissue paper. But even Jupiter's monstrous belts are dwarfed by what happens when a star, not a planet, starts trapping particles of its own. Magnetars produce radiation environments that make planetary belts look like static electricity. A magnetar is the collapsed core of a massive star packed into a sphere roughly 20 kilometers across, spinning with a magnetic field trillions of times stronger than anything Earth can generate. Around a magnetar, charged particles are not just trapped, they are accelerated to extreme energies. Within a magnetosphere that can extend thousands of kilometers into space, the magnetic field is so intense it can distort the very structure of atoms that drift too close. Discovered through their extreme bursts of energy in the late 20th century, magnetars remain some of the most magnetically violent objects ever measured. But the next entry on this list does not just trap radiation. It generates it in pulses precise enough to set your watch by. Pulsars are the spinning remains of collapsed stars, and their radiation belts are shaped less like a donut and more like two narrow blazing beams, sweeping through space as the object rotates. Some pulsars spin hundreds of times per second, meaning their radiation beams sweep past a fixed point, with a regularity more precise than most man-made clocks. If Earth sat directly in the path of one of these beams at close range, the radiation would overwhelm any magnetic shielding a planet could naturally produce. The first pulsar was identified in 1967, and the discovery briefly puzzled scientists because the signal was so mechanically perfect. It did not initially look natural. So if a spinning star can aim radiation like a lighthouse beam, what happens when an entire star system gets caught inside one of these belts permanently? That question brings us to close binary systems where two stars orbit so tightly that their radiation belts and stellar winds collide and merge into a single, shared danger zone. In these systems, any planet caught between the stars would sit inside overlapping fields of charged particles, constantly interacting and intensifying each other. The radiation environment becomes unpredictable, spiking without warning. As the two stellar magnetic fields twist against one another, no stable belt, no safe orbit, just a shifting storm of energy with nowhere calm to hide. If you have made it this far into the universe's most dangerous radiation zones, this is the point where the list stops being about individual objects and starts being about entire regions of space. Drop a like now, because the next entry does not belong to a star at all. It belongs to the empty space around a black hole. Around actively feeding black holes, matter spiraling inward forms what is called an accretion disk, and the radiation pouring off that disk creates one of the harshest environments in the universe. As gas and dust are pulled toward the black hole, friction and gravitational compression heat the material to millions of degrees, and the radiation belt that forms around this disk can extend for millions of kilometers. Unlike a planet's belt, this one is constantly fed by new material falling in, meaning it never weakens and never stabilizes. Get too close, and radiation alone would overwhelm you long before gravity became the more immediate concern. No warning, no shielding thick enough. Just an expanding wall of energy radiating outward in every direction. But even this is not the most extreme radiation environment tied to a black hole. Consider what happens near a black hole releasing a relativistic jet, a narrow beam of particles blasted outward at close to the speed of light, from the poles of the black hole's spin axis. These jets are among the most energetic phenomena scientists have ever measured, carrying radiation levels that dwarf even the accretion disk itself. If a jet like this were pointed directly at a planet from a relatively close cosmic distance, the radiation could strip away an atmosphere over time, leaving a world exposed and lifeless. The common assumption is that a black hole's danger comes purely from its gravity, from the point of no return at its event horizon. But that assumption misses the point entirely. For many black holes, the radiation reaches out and does damage long before gravity ever gets the chance. Now consider a supermassive black hole, one containing millions or even billions of times the mass of our Sun, sitting at the center of a galaxy. The radiation belt and jet systems around these giants operate on a scale that makes stellar black holes look almost gentle by comparison. Sagittarius A star, the supermassive black hole at the center of our own galaxy, is relatively quiet today, but supermassive black holes in other galaxies have been observed powering radiation output, bright enough to outshine every star in their galaxy combined. A galaxy caught in the path of one of these active radiation zones could have its most habitable regions rendered uninhabitable, not by an explosion, but by a slow, continuous bath of high-energy particles. And somewhere in the dark spaces between galaxies, there may be a radiation environment stranger and older than any of these, one connected not to a single object, but to the structure of the universe itself. That brings us to the cosmic ray background, the faintest but most far-reaching radiation field of all. Cosmic rays are extremely high-energy particles that travel through the universe at nearly the speed of light, originating from supernova remnants, active galactic centers, and sources that remain only partially understood even today. Unlike a belt trapped around a single object, cosmic rays saturate the space between galaxies, meaning almost nowhere in the observable universe is entirely free of them. A planet without a strong magnetic field and thick atmosphere, like Earth's, would have no real defense against this constant low-level bombardment over long timescales. We have measured cosmic rays reaching Earth with energies far beyond what any human-built accelerator has produced, and we still are not entirely certain what created the most extreme of them. No boundary, no edge, just a quiet and permanent hum of radiation woven into the fabric of the cosmos, older than most of the stars in the sky. That is the ladder from a belt small enough to orbit one planet, to a radiation field vast enough to fill the space between galaxies. Every world we have ever called home sits inside a narrow, fragile pocket of calm, protected by nothing more than a magnetic field and an atmosphere, thin enough to fit inside a rounding error on a cosmic scale. If this list made you feel smaller than you did 5 minutes ago, that feeling is accurate. Subscribe before the universe finds a way to remind you just how thin that protection really is, and if you are not ready to return to normal space just yet, the next video on this channel is waiting for you. One dark step further out.